Thank you, Dr. Ochoa. Yeah, so today I'm talking about the effects of dairy manure application and wheat straw residue coverage on runoff and infiltrate and agricultural soils. And like he said, this funding came from the NRCS for this project, and it's much larger than what is shared today. But what is being shared today primarily focuses on understanding how agricultural management practices influence water movement, soil erosion, and water quality. So before I get into the nitty-gritty, there we go. I want to do acknowledgements. This photo was taken on my first faculty-led program to Puerto Rico. It's also where I met Wanda Cornell, who during this trip really sold the BRR program to me. And so this is kind of a symbolic photo to what's currently now with where I am and about to finish the program. So thank you, Wanda. Next, of course, the Eco-Hydrology Lab, how Dr. Carlos Ochoa mentioned that this isn't a one-man project. It's encompassed by many master's, PhD, and undergraduate students. So I want to acknowledge that their time and effort did not go unnoticed. And then, of course, my family, especially my parents, they listen to me a lot. They don't know what I'm talking about, but I really appreciate their ears all the time. And then my roommates, of course, they're in the back. So happy they're here, and their support is never unnoticed either. So throughout this presentation, I have 7 different sections, starting with the background, a little bit of why this is relevant, and then into the introduction, which is more specific to Oregon, followed by our objectives, and then the methodology throughout this project with our results, and then discussion and conclusion further from there. So starting off, I have this figure provided from the Intergovernmental Panel on Climate Change. It talks about sudden food production loss from their 6th assessment report. As you can see in the purple hexagons there, those are increased storm events around the world. These increased storm events are now cutting food growing processes beyond safe climatic space for production. So it raises concerns over like what we can do to help fight climate change within the agricultural system. So within the US, land change occurs for a variety of reasons, whether it's change in commodity to change in timber prices, but around 53% of land use in the US is based for agricultural purposes, things from cropping, grazing, and farmsteads and farm roads. And in 2017, grass pasture and range was actually the highest for a million acres, which is on your Y, and you can see the grass pasture and range in the navy blue on 2017 all the way to the right. And when we're talking about total cropland used for crops in the United States, in 2024, about 328 million acres of land were used for crop production, with around 303 million acres that were actually harvested. This is because of crop failure or cultivated summer fallow, which is why there's a differential in the amount of acres used versus the amount of harvest that was produced. And so since we're talking about manure application, it's also important to acknowledge a cow's contribution to US agriculture. So in 2022, there were about 9.3 million milk cows in the United States. Over 41% of the US land is used for cattle, with an average farm size being about 483 acres in 2022. And so with all that in mind, I'm going to move to the introduction of why that information is relevant within this project. Starting off, since we are located in the Willamette Valley, it's important to acknowledge the land use here. So agricultural land management practices can strongly influence soil erosion, surface runoff, and water quality. And land variation within the Willamette Valley varies, as you can see in the figure here on the right. It can be anything from wetlands to open water, oak savanna, with agriculture being the largest, and then urban forest and more. Within the valley, we also have various different commodities. There are actually more than 170 agricultural commodities in the Willamette Valley, ranging from grass seeds, fruits, nursery crops, vineyards, dairy cattle, beef cattle, sheep, poultry, and more. And in 2005, the Willamette Valley had around 66,400 beef cows and nearly 280,000 calves and cattle itself. So now to talk a little bit about rainfall in Oregon and why we'll be using a rainfall simulator later within our study. So the Willamette Valley is located west of the Cascade Range, which is split off by the color changes. So we're in the green, and then the coast is all the way on the left, and then the red-orange side is east of the Cascades. As you can see on this scale, the purple is where the heaviest precipitation falls in the state of Oregon, and the red is where the least amount of precipitation falls in the state of Oregon. So this shows that areas near the Coast Range experience some of the highest rainfall totals in the state, which increases the risk for surface runoff, soil erosion, and nutrient transport. And rainfall intensity plays an important role in sediment detachment and transport as it intensifies precipitation events and can accelerate runoff velocity. So when we talk about benefits of manure application, animal agriculture, specifically dairy production, contributes to large quantities of manure that must be managed sustainably. So dairy manure consists of undigested plant residue and can be applied to agricultural fields as an organic fertilizer source. So as you see on the right side of the screen, dairy manure has nitrogen, phosphorus, potassium, and sometimes even organic carbon. According to a research study, about 70 to 80% of nitrogen, 60 to 85% phosphorus, and 80 to 90% potassium that is excreted by the cow can be used as a nutrient source for a plant. In the infographic, you see that once a cow, chicken, or pig excretes fertilizer, it's initially in an organic form, but through the process of mineralization, it becomes inorganic, which makes it available for plant uptake. So unlike synthetic fertilizers, dairy manure contains organic carbon, which can also improve soil structure, enhance cation exchange capacity, water holding capacity, and overall soil health. And so some of these examples are shown here. First one, water holding capacity and soil structure. With the improvement of soil organic matter, it also improves the soil ability to retain the water. And since the organic matter helps act like a sponge, the storing water that can be used later for plant use is also present. It also improves soil aggregation, which helps create more stable soil structure while enhancing the pore space. For our cation exchange capacity from the benefits of manure examples, basically cation exchange capacity is a measure of the soil's ability to hold positively charged ions. It's very important for soil properties because it influences soil structure ability, nutrient ability, and soil pH, all which helps with the soil's reaction to different types of fertilizers. It also influences the soil's ability to hold essential nutrients and provides a buffer against any soil acidification. And of course, manure application has challenges, the first one being the odors from the volatile compounds. While it's more of a social and public health concern, it's something that you can't ignore. And then sediment transport and runoff that can carry those attached nutrients into nearby waterways that could affect water quality. So throughout this process, there's a mechanism of water erosion called splash erosion. It's basically when the kinetic energy of the raindrop dislodges the soil particles, and the result is that runoff transports the soil particles. So in the picture, you see how the raindrop hits the soil, it dislodges soil particles, and those get transported downstream and then decompose at the very, very bottom. This also has the ability to block the spaces between the soil aggregates so that the soil might form a crust that even reduces infiltration and runoff even more. Within the study, I'll be talking about total suspended solids, also referred to as TSS. It refers to waterborne particles that exceed 2 microns in size. It could be anything that floats or suspends in water, like sand, sediment, or plankton. In the picture, you can see on the very left, that's pretty clear water, but on the picture on the very right, it's darker water, which kind of implies there's more suspended solids within that cylinder. So crop residue acts as a protective barrier because the residue cover slows down surface runoff. Less runoff means less sediment and nutrient loss, and more residue coverage can improve water quality for soil conservation. Second. There we go. So within this project, I'll be referring to something as crop residue. If you don't know what crop residue is, it's the portion of the plant or crop left behind on the field after harvest, or the part of the crop that is not used domestically or commercially. It helps enhance the soil organic matter, release nutrients back into the environment or into the soil, and then improve soil fertility and structure. For its relevance in our project, it is because wheat straw is widely used across Oregon for animal bedding, erosion control, and garden mulch, which is why we're using it as our crop residue cover. So now on to our objectives. We have 2 main objectives here. The first one is to assess the impacts of crop residue cover from 0%, 50%, and 100%, and then to assess the impacts of manure application rates 0, 20, 40, and 60% of kilograms of phosphorus per hectare on infiltrate and runoff water partitioning and TSS in runoff, as well as using a rain simulator by applying 1 inch of rainfall of 1 inch of rainfall of water in 6 minutes. Whoa, that was a tongue twister. So now onto the methods. First is our soil site collection. We collected soil from the Oregon State University Student Organic Farm located here in Corvallis, Oregon, which is in Benton County. The soil type was Chehalis, and basically that soil is located in Mediterranean-influenced marine climates characterized by wet, mild winters and warm, dry summers. Its main uses are for crop production, hay production, and livestock grazing in cleared areas, as well as even for wildlife habitats. So for our sampling method, we collected soil from the top 30 centimeters, and then multiple samples were taken within a 3.2 square meter site to get a representative of a bulk sample. We then did a soil texture analysis, which tells us the relative proportion of sand, silt, and clay present in our soil. The soil texture we got was sandy loam. This was because there is 55% sand, 31% silt, and 14% clay present in our soil. And so you might be asking yourself, why sandy loam soil? This is just ideal for most soils because it has a high fertility as well as a deep and well-drained soil type found along floodplains. It also has excellent drainage. It's easy to work with, very versatile from lawns to growing vegetables in your gardens. I also think I read somewhere that people use it in construction as like bases for foundations, but also it has good aeration for the roots to breathe. So from there, we did soil tray preparations after we collected our soil. So the soil was laid out to dry for 7 days in an outdoor ambient temperatured area. From there, the soil was sieved to 1.3 centimeters or half an inch to remove any large rocks, aggregates, or debris. You can kind of see the milk carton here up in the right. That was our makeshift sieve with some chicken wire on the bottom. From there, we did our soil tray preparation where the soils were packed to bulk densities to represent the student organic farm site. Basically, the soil was applied in layers and tampered for even distribution. And it's also important to acknowledge that all soil trays were the same size. They're approximately 2.5 inches tall, 12 inches wide, and 23.5 inches long. From there, our manure was collected from the Oregon State University Dairy Research Center. Basically what they do is they have a waste stream that directs into a separator where the solid and liquid fractions of manure are separated. And so the liquid manure has residual manure and urine leftover. And then the soil particles the solid particles are separated out. And then once they separate them, that liquid manure goes to an open air tank prior to collection. So within our method, we had 4 different variations within our soil trays. The first one was just soil only. Sometimes I might refer to it as bare soil. Our next one was soil and manure at the 20, 40, and 60 kilograms of phosphorus per hectare rate. And then our next one was the soil and then the 50% crop residue, and then that same manure applied at that 20, 40, 60 kilograms of phosphorus per hectare rate. And then finally, our last one was soil and then 100% crop residue cover at that same manure applying rate in kilograms of phosphorus per hectare. And to kind of give you a real life visual of this, if you look on the screen from the very left, that's 0% cover and no manure applied. And as you go all the way to the right of the screen, you can see the manure is increasing in those increments, but the 0% coverage is staying the same. And then similarly, again, but with crop residue variation, you can see that we are holding the manure levels at the same kilograms of phosphorus per hectare application process, but instead the coverage is varying. So there's no coverage on the very left all the way to 100% coverage on the very right. From there, we would put our soil trays through a rainfall simulation. These were conducted every 7, 14, 21, and 28 days after the liquid manure was applied to the soil trays. And the trays were positioned at a 4% slope to promote runoff. And we believe the 4% slope was a good replication of what's in the real world, because if you think about it, not all agricultural fields are flat. So there is a slope to help with variations in rainfall, runoff, and infiltrate. I also wanted to provide a schematic here to help you understand the bottles that are under our rainfall simulation. Basically, the ones we have in the front that are that dark brown colors for any runoff. Runoff is basically anything that goes off of the top of the tray and slides off the soil. And then leachate or infiltrate is the stuff that goes through the soil. I kind of like to tell people it's what happens when you water like the little pot you have in your windowsill at home, like whatever collects on the tray below, that is infiltrate. And then here's the rainfall simulation in action with the varying coverages. As you can see as well, those runoff and infiltrate bottles I was just talking about are present there. So on the very left, there's no coverage, and then on the very right, there's 100% coverage. Once we conducted our rainfall simulations, the runoff jars were removed immediately after, and then the infiltrate jar sat for an additional 10 minutes. The jar's volume was determined by measuring the height and weight, and then subsamples from the runoff, which is shown here. They would take a 500 milliliter bottle and then 250 milliliter bottle for the infiltrate for analysis. With those samples, we would then do what is called a total suspended solids test. It's an EPA approved method, I believe created in 1999, but basically what happens is you filter a known volume in the top on a pre-weighed filter, and then whatever's left over after the water is filtered through, you can put in the oven through a drying method, and that can let you know the amount of residue that was in a set amount of volume. So now on to our results for the whole study. First off, we have our water partitioning, which is basically just where did the water go? So did it slide off the top through runoff, or did it go through the soil tray and be called leachate or infiltrate? So basically this graph here is the cumulative infiltrate in blue and runoff in green partitioning for the simulated rainfall events from week 1 to week 4. So as you can see, the rainfall timing had a significant influence on the water partitioning. The infiltrate volumes remained relatively steady. From week 1, you can see it's at about 22.6. The lowest is week 3 at 18, but they all stayed relatively the same. And then runoff volumes continued to increase as the weeks increased. For the effect of crop residue coverage on infiltration, this graph here shows the cumulative infiltrate partitioning from simulated rainfall events based on crop residue coverage. So the blue is for 0%, the green is for 50%, and then the 100, or the purple is for 100%. And we can see that across all 4 simulations, 100% cover consistently produced the greatest infiltration volumes, then followed by 50% coverage, which is in green, and 0% coverage, which is in blue. And so the trays without cover crops had the lowest infiltration, which indicated more water was lost through runoff, while 50% coverage improved infiltration, but 100% coverage was the most effective treatment. So now the effect of crop residue coverage on runoff. Similar graph, except now we're talking about what slides on top of the tray instead of what goes through it. So during weeks 1 and 3, we can see that 100% coverage produced the lowest volumes, which is the one in purple for those first 3 purple bars. And then 50% coverage throughout the whole week showed variable performance. This is just because sometimes it was higher, sometimes it was a little lower. And then during week 4, runoff increased under 100% throughout all coverages, resulting in higher runoff than we initially expected. And then effects of TSS from rainfall events. We see the impact of crop residue on total suspended solids here in this graph. So again, 0% is that blue, 50% is the green, and then 100% is the purple. TSS is in milligrams on your y-axis. And this shows that crop residue coverage was highly effective at also reducing erosion, and that TSS decreased substantially as crop residue increased, with 100% coverage clearly providing the greatest protection against sediment loss. So when we put all of that information together with all of our rainfall events, we get a big crazy graph like this. So basically, I want to walk you through the x-axis. So we have coverage and then rate. So over here, for instance, these are all 0% coverage with our varying rates of 0, 20, 40, 60. Similarly here with the 50% coverage, and then we have 0, 20, 40, 60 kilograms of phosphorus per hectare. Same thing over here with our TSS still in milligrams on the y-axis, which is basically just telling us how much soil was actually lost throughout our process. So overall, we can see there's a decline in TSS as our crop residue increased. We have an R-square valued on this line about 0.9 or 0.89, which is really, really good. And this just shows how if you increase crop residue coverage, the TSS will decline. When focusing on coverage-specific areas of TSS from rainfall events, we see that 0% coverage produced the highest sediment loss values in TSS, with manure applications helping reduce TSS on bare soils, which we can see because as you are applying the 20, 40, 60, there is a slight decline here, even though these still overall are high TSS ranges. And then when we go to the 50% coverage, there's a larger impact on coverage than the manure played in this factor, which you can see as the TSS values are slowly declining, but they're still relatively high. And then finally, TSS had the lowest values for 100% coverage, which you can see here on the very, very right, where they're very, very minimal. So this is the same graph, except now it's talking about how muddy the runoff water is, and this y-axis is just in a different unit of milliliter or milligrams per liters. And I was looking into it, and while there isn't a set number of like what is deemed like extremely dirty water, we know that typical storm water is about 20 to 100 milligrams per liter of TSS, and our values are ranging from about 20,000 to 22,000 milliliters of TSS, which is significantly high when we're talking about water quality, but it shows that unprotected soil can lead to severe sediment loss. So now with our discussion, I have this graph up here just to help you kind of understand what I'm saying, but it's not any new data. Again, with the cumulative infiltrate in blue and the runoff in green from our simulated rainfall events ranging from week 1 to week 4, we see that rainfall intensity exceeded the infiltration capacity of the Chehalis sandy loam soil here. We know that because the numbers for infiltrate in blue are staying relatively the same. And then runoff volume suggests that manure and crop residue coverage was an increase in water within our system every single week. So when we talk about water partitioning in this case, we also are acknowledging that increased runoff has important environmental implications. So practices that can increase infiltration and reduce runoff can also help improve water retention and can reduce erosion and protect downstream water quality. This highlights the importance of land management practices that can help increase in that infiltration and reduce the runoff and reducing the water pollution. Something important to note is that this study used, actually, I'm going to hold that off. Okay. So when we talk about water partitioning, I wanted to include a photo up top of a wetland, and I wanted to include that because increased crop residue helped improve hydrologic function with higher infiltration and lower runoff across all simulation events. And I kind of envisioned it like a wetland, like the water sits there because there's stuff to hold it in place. And in our case, we kind of use crop residue to hold water in place. And so in terms, that was our way of mimicking a real world event. So we saw that 100% crop residue had the best infiltration rates into our soils, and that the 0% crop residue showed the lowest infiltration, probably due to compaction and surface sealing from the movement of soil particles. Within the impact of crop residue on total spended solids during our simulated events, we saw that crop residue was a dominant factor in controlling our sediment loss, presented here clearly on our graph, where the TSS that is on the 100% coverage in purple is way lower than the TSS that's presented in blue for 0% coverage. And full coverage or full residue coverage also reduced variability in sediment loss between our rainfall events. We see that again with the purple being very similar low numbers. So basically, what we like to call TSS is a nutrient vehicle, because if we had bare soil, there'd be higher TSS, and wheat straw coverage provides lower TSS, because if there's bare soil, then we'd have a higher nutrient loss, and then the wheat straw coverage helps reduce our nutrient loss. So when we talk about sediment loss, we saw that manure application influenced sediment loss under some conditions, but residue coverage overall had a much greater impact on our soil erosion, and that crop residue coverage is important for protecting water quality, especially during those high intensity rainfall events. It's also important to talk about our rainfall simulator relevance, because we used it as an extreme rainfall event. So if it was to be rerun under different conditions, the effectiveness of crop residue coverage may have different outcomes. But it's important to acknowledge that climate variations are happening, And so management practices are important to improve infiltration while protecting soil and water quality. With our study, there are some limitations. Soil tray depth, we were curious if you could deepen the soil tray, if it could tell you different results based on our infiltrate numbers, as well as we had a short study duration. While 4 weeks might seem long, in a project like this, what would 8 weeks do? And then we had a limited manure type just because dairy manure was easily accessible to us, but it'd be interesting to see how different types of manure could impact our rainfall simulation results. And then, of course, our rainfall simulation conditions. We're using extreme weather event. Be interesting to see what a normal rainfall event in the Willamette Valley would have on our results. And finally, for our discussion area, or for our conclusion, we had 4 major key takeaways. The first one was that crop residue coverage was the most impactful factor in reducing sediment loss. This was because 100% residue was constantly producing the lowest sediment loss. And then residue improved water management, where the surface residue protected the soil from the raindrop impact, like that splash erosion we were talking about, and slowed water movement across the soil surface. And intense rainfall events can generate significant sediment loss. This highlights the importance of physical protection within our study on soil surface and the influence erosion has with the connection to manure application rates. And then managing ground cover, that is an efficient strategy for protecting water quality because it's important to understand management practices if you were to experience a severe weather event. And so overall, the study demonstrates the importance of maintaining crop residue coverage. So what we know, though, at the moment is that crop residue plays an important role as a protective ground cover. It also safeguards against erosion, captures moisture, and provides food for soil organisms. And with that being said, if you have any questions, let me know.